Welcome, systems architects and developers. Think of this as the ultimate coding challenge. In this explainer, we're going to treat the current physical operating system of the universe itself like a codebase and explore exactly how we might optimize it. If you've ever wondered how the absolute fundamental laws of physics dictate the hard limits of human technology, specifically when it comes to data storage and transmission, well, you are absolutely in the right place. Okay, let's just dive right into this pursuit. We're going to translate high-level theoretical physics into actionable API documentation for your universe simulator. We are going to treat physical laws not as these abstract, untouchable mysteries, but as hard-coded constraints and actual software protocols. And as any good software engineer will tell you, once you understand the constraints of a system, you can start hunting for the exploits. So, here's our sprint planning agenda for today. We'll be hitting 1. Architecture of cosmic systems. 2. Universal causal data throttles. 3. Quantum error correction protocols. 4. Inverse speed metric exploits. 5. Warp metrics and data routing. And finishing up with 6. Quantum network deployment roadmap. Let's kick things off with Section 1, Architecture of Cosmic Systems, and identifying the baseline conflicts. To build our simulator, we really have to establish the fundamental incompatibility currently sitting in our source code. We're talking about the famous contradictions between general relativity, the macro level, and quantum mechanics, the micro level. Think of general relativity as the stage. It's smooth, it's continuous, it's deterministic. Then you have quantum mechanics. These are the actors on that stage, and they're totally discrete, highly probabilistic, and their fields fluctuate violently. This mismatch causes what physicists call the ultraviolet catastrophe bug. It's essentially a fatal divide by zero error. If you try to calculate quantum fluctuations at a zero distance point on that smooth stage, it yields infinite energy densities. Basically, it just completely crashes our system. Moving right along to Section 2, Universal Causal Data Throttles and Interpreting Physical Laws as Software Protocols. Let's look at physics as protocols and see how this builds into the physical hardware limits that govern data latency across our simulated networks. Every system has a bandwidth limit, right? The universe is no different. But the crucial point here is that the speed of light, what we call c, isn't just a velocity limit for a physical mass flying through space. From an architecture perspective, it's actually a hard-coded causal latency throttle for routing data packets. It's literally the maximum clock cycle speed at which one point in the universe can update the point immediately next to it. If you try to route data faster than this, you completely violate standard causal chronology. You essentially create a fatal error where a packet arrives before it's even sent. No way around it. Which naturally leads us to a massive engineering bottleneck. If we pack too much data into a physical storage medium, the energy density triggers something called the Bekenstein bound. If we push past that limit, the local gravity well collapses our storage hardware into a black hole singularity, a literal physical hardware crash where all your data gets erased. So, how in the world do we engineer a workaround for a hard-coded physical limit? That brings us to Section 3, Quantum Error Correction Protocols, and looking at the universe as a fault-tolerant system. To engineer that workaround, we first have to understand how the fault-tolerant universe itself behaves as a massive error-correcting computing system to prevent packet loss. Because the quantum environment is so incredibly noisy, data payloads are constantly at risk of decoherence. Because the laws of physics flat out forbid us from simply copy-pasting a state, thanks to the no-cloning theorem, we have to map topological surface codes directly to lattice grids. We distribute one logical bit of information across many entangled physical states using non-local entanglement distribution. By running continuous syndrome measurements on these codes, the system can actually detect and fix phase flip errors without collapsing the underlying data. It's brilliant. Okay, and here is where it gets completely mind-bending. The source material reveals that the 3D continuous geometry of spacetime is actually an emergent projection of 2D quantum fields. It acts just like a radical quantum error-correcting code, essentially a cosmic RAID array. What this implies is that our macroscopic physical stage is actively being held together by microscopic non-local entanglement. It automatically buffers local anomalies and noise to protect the grand cosmic code from crashing. So, the universe itself is inherently fault-tolerant. Now we can pivot to the really speculative release branch in Section 4, Inverse Speed Metric Exploits, where we explore shifting data blocks out of band. This is where we analyze how inverse light speed theories challenge and attempts to completely rewrite that causal data throttle we talked about earlier. Instead of looking at distance over time, what if we flip it? By promoting the inverse speed of light, or the slowness parameter, s, to a fundamental matrix, we can mathematically manipulate the metric. If we can operate a system in a hyperdense sub-inverse phase, meaning it's moving slower than the inverse speed of light, we decouple the wave packet's clock rate from traditional light cones entirely. The data payload basically becomes a stationary, hyperdense phase. By mapping geometric manifold distortion directly to data transmission speeds, we find two distinct protocols. First, if we want hyperdense storage that bypasses that pesky Bekenstein bound without creating a black hole, we need sub-inverse phase compression. This requires localized negative energy, something like what you'd extract from a Casimir grid. On the other hand, if we want latency-free, out-of-band data routing, we need tachyonic phase tunneling, which utilizes squeezed quantum fields. Let's dig deeper into that in Section 5, Warp Metrics and Data Routing and Compressing the Expansion Scalar. Speculative Alcubarier warp metrics physically route these data packets by mathematically bypassing spatial degradation altogether. This is where we stop pushing data through space and actually start moving space around the data. The Alcubarier line element dynamically compresses the metric ahead of a data vector and expands it behind it. We're engineering the local stress energy tensor to translate the coordinate envelope itself. By utilizing non-commutative geometry, where the actual order of spatial coordinates fundamentally alters the state, we can allow for subspace data transmission. Because the space inside the bubble remains completely flat, the data payload experiences absolutely zero kinematic time dilation. There's no spatial degradation, and time of flight latency drops straight towards zero. But to pull this off in reality, we have to violate the weak energy condition to generate localized negative energy density. How exactly? Well, by deploying 10 nanometer Casimir grid extraction plates to create a net negative vacuum pressure, or by pumping nonlinear optical fields to basically squeeze quantum noise. This is the mathematical requirement to manipulate the metric and successfully bypass our current universal causal latency limits. All right, final sprint, Section 6, Quantum Network Deployment Roadmap, going from theory to network infrastructure. We're going to translate these theoretical quantum protocols into a practical, step-by-step roadmap for building high-speed network infrastructure. But we hit a huge roadblock when we try to deploy this. The universe has a built-in firewall. It's called the quantum inequalities subroutine. If we hold a negative energy state open too long to transmit our out-of-band data, the universe forces a massive positive energy backlash that will literally fry our hardware. So, we have to deploy a fragmented timeline. We send data in picosecond bursts, instantly followed by nanosecond positive energy cooling cycles. It's basically pulsed asynchronous routing. But sending packets in fragmented picosecond bursts? That causes severe synchronization issues. To resolve this, we deploy the ER equals EPR protocol, the principle that entangled quantum particles are literally connected by micro wormholes. We map these Einstein-Rosen geometries directly onto macroscopic topological entanglement networks. So we bypassed free space tunneling entirely to create hardwired, non-local data links. The data packets aren't traveling through space. They're traversing the non-local throat of the bridge, which keeps their quantum phases perfectly synchronized. As you go out and architect the systems of tomorrow, keep this at the absolute forefront of your mind. Physical laws are not these mystical, unbreakable barriers. They're simply hardware constraints waiting for the right software exploit. So, when your data storage hits the ultimate threshold, what's your play? Are you going to let the system crash, or will you engineer the underlying code to expand reality itself? Something to think on. Thanks for joining me on this explainer, and keep pushing those boundaries.